Now let's go to the real definition of transformation. Well, transformation always, if you go to the high dimensional, it is a map between n dimensional space to m dimensional space. When you need that map, well, look, we have a rounded sphere Earth. If you want to draw the map in the paper, you draw it flat. That's a transformation. We need to flat the whole Earth. And so you basically, you are doing a 3D transformation to the 2D. And then the rounded Earth is kind of cut line by line like this and spread. That's how you see the map. So generally involve n input parameters and the m output parameters. That's our real world. It's not a 1D to 1D function. Now let's give an example. And this is a simple one from 2D, x1, x2 is just 2D, to the 3D, which is W1, W2, W3. And if you look, the first row, 3x1, negative 4x2, I write into matrix, 1x1, 2x2, and the last one is 6x1, negative x2. So how do you use it? If I give you the x1, x2 equals negative 5, 2, and then you're going to multiply this 3, 1, 6, negative 4, 2, negative 1, and well, then when you multiply, you're going to get this number. Or you can write it into a column, should be a column. Negative 23, negative 1, negative 32. Let me just do one, you're going to see it. 3 times negative 5 is 15 negative. So wait a moment. 3 times negative 5, oh yes, negative 4 times 2 is negative 8. That's negative 23, that's this element. You know how to multiply, that's all you need to do. The next one will be different. It's also a transformation. This time, you go from the 2D, the 3D, to the 2D. The only difference I want to emphasize here, you look at those squares. When you have those squares, we call it nonlinear. And then the calculation is the same. You simpler, if you know this x1 equals 3, x2 equals negative 1, and x3 equals 6, you just plug in the number to here and here, you are going to get the two numbers. That's the algebra. So the emphasis here is the linear transformation. The linearity, I call it linearity, is a property that have two important properties. The first one, we call it the addition property. The addition property, when you have the transformation of the addition here, it equals the addition of a transformation. If you read it now, transformation of addition equals the addition of transformation. And the second one, we just say if you multiply a constant, you can pull out the multiplication, the c. This we call it the multiplication property. Any transformation, if satisfy these two properties, they're very nice. You can always write this transformation as a matrix that all constant number times x. We're going to learn more later on, but let's look at the example. First, I want to prove is the projection is a linear transformation. And look at this one. We need to prove if you add the two vectors first to get the z, and then you transform the z as the projection, you're going to get this one. Or, another way, you first project it first, this y projected to here, the x projected to here. When you project first and then you add, you get the same v. So what I'm saying is you do the calculation, you find you can add first, do the projection, or projection first, then you add, you get the same result. Let's do it. Now the x is 1, 1, y is 1, 2. When you add, it's 3, 2. This vector is 3, 2. But if you project first, you get this. Project the y first, you get this. But if you add this 2, if you add, what you get? You get the same 1/10. And 4 plus 5 is 9. 15 plus 12 is 27. Equals exactly the same. You add first, you projection. And this is project first, then you add. Same thing. That is the rule here. You need to have this additional property. And the multiplication property is very simple. If you get the z, you got a half z here, you projected it, it's just half of the projection. That's the easy thing. So the projection is a linear transformation. Everything today we talked, except the example a moment ago with a square, are linear. Okay, let's look at another two examples. The first thing is the rotation. The most frequently used transformation in computational geometry in any robotic navigation is rotation. The first thing is that's linear. The proof is the same. If you make it longer, you rotate, or you rotate first, make it longer, with the same multiple, they equal. In here, you can add the vector first, then you rotate, or you rotate first, then you add. That's the same thing. So that's a nice linear properties. Well, the next, I got this simple rotation to see how we're going to find the matrix. The idea is this. We start from the unit vector along x direction. Then we rotate theta to see what we get. This is a simple trigonometry. When you rotate, the unit vector is still unit vector, means the length is still 1. And now if you assume the coordinates x1, y1, and then see the x1 over the hypotenuse, which is the adjacent over hypotenuse, you got a cosine. Then you got the x equal cosine here. And the x equal cosine. Also, if you look at the y1 over the hypotenuse 1, you got the opposite, the sine theta. The sine theta, then you got the y equal sine theta. Okay? Then the rotation of E1 to an angle theta, you got a cosine theta, sine theta. how do we rotate the E2? The E2 is the unity vector at the y direction. No, that's 0, 1. So the only difference is pi over 2. You rotate the E2 by theta equivalently, you rotated the E1 vector by theta plus pi over 2. And then I use the same formula above, but change the angle to pi over 2 bigger. And by trigonometry, I got this negative sine theta, cosine theta. So basically, transform the E1, I got this cosine sine. Transform the E2, rotate, I got the negative sine cosine. So look what we can do with that. Now back to any arbitrary vector. By the projection form, the vector can be written as x1 times the first unity vector plus x2 times the second. Now, we use the linearity of transformation. Tx then equals T of this addition. This addition, by the addition property, we can transform first, then add. By the multiplication property, this x1 can get out. That's what you have. And this x2, again, is a number. You can get it out. That's what you get. So whatever x be x1, x2, all I need is add multiple x1 multiple of the first transformation we got a moment ago, and the x2 multiple of the second transformation. And then we can write it into this form. This is a two-component vector, and this equal this rotation matrix times the x1, x2. If you have hard time, you just multiply back. Cosine theta times x1 is this term. Negative sine theta times x2 is this term. You just add. The second one, sine theta times x1, this is the term. And you know it's a dot product, times cosine theta times x2 is this term. So what a beauty. When you do a rotation, all you need is to multiply this matrix. And then you did the rotation. So let me show you a simple example. If I have a vector, this is 2, 4. Now I can draw the 2, 4. 1, 2, 4 is here. If I want to rotate this by pi over 3, and then it's going to be here. That's pi over 3. So what is the coordinate of this new one? Well, if you use the Euclidean geometry, it's quite a challenge. But now you learned, all I need is to multiply this matrix to this vector, and even you do by hand, it's a few seconds work. See, 1/2 times 2 is going to be 1. Negative square root of 3 over 2 divided times 4 is going to be plus negative 2 square root of 3. And the second row, this times 2 is going to be square root of 3. 1/2 times 4 is going to be 2. It's right here. You're done. So I know if this is 4, 2, my new vector, it's going to be 1 minus 2 square root of 3 for the x, square root of 3 plus 2 for the y. Accurate. Quicker. Now we go to the complicated one.